Welcome back to the Lowdown on Physics. This is screencast number 5 in Unit 3 VCE Physics, Motion, 2 and 3 Dimensions. Today we will be considering frames of reference. So I want you to just stop and think for a second before we go any further. Question. Is the velocity of an apple thrown into the air when driving a car at 100 km an hour the same as the velocity of an apple that's thrown in the air when the car is stationary? Why or why not? The answer is yes and no. It all depends on where you're observing the apple from. Are you observing it from inside the car or outside the car? And where you observe it on will change the appearance or the velocity of the apple. You see, when we're discussing velocity of an object, usually we refer to the Earth as the frame of reference. So how fast it's going is compared to how fast it appears to be relative to a stationary Earth, which is technically not stationary. So what we're using is what we call an inertial frame of reference, and that's one where it's free from acceleration. So it's either stationary or it is moving at constant velocity. So Newton's laws of motion are valid at slow speeds, we're talking hundreds of kilometres, that's fine, and they need to be within an inertial frame of reference. Take it outside of an inertial frame of reference, that is at acceleration, and they no longer work. So what we're actually referring to when we're looking at the apple and the car, whether it's stationary or whether it's moving, is something that we term a relative velocity. So let's consider two trains. We have train A, who's travelling to the east, 15 metres per second, and we've got train B travelling to the west at 10 metres per second. What's the velocity of train B relative to train A? What that means is, if you're sitting in train A, how fast does it appear that train B is moving? In order to answer this sort of question, the easiest way is to set up the following equation. And that is to look at the velocity of B relative to A as the difference in velocity B and velocity A. So velocity B minus velocity A. And that's really just a vector question then. It's a simple vector problem once you establish what you're doing. So you've got velocity of B minus velocity of A. When we subtract vectors, we rotate the subtracted vector and then we add them. So ultimately, once we add that, velocity of B relative to A will be 25 metres per second to the west. So it raises a question, why are head-on collisions so dangerous? Okay, so consider another example. We have a person on train A who stands up and walks to the front of the carriage at 2 metres per second. And train A is travelling at 35 metres per second relative to the ground. What is the velocity of the person relative to the ground? Well, if the train's moving at 35 metres per second and they move at 2 metres per second on that train to the front, then it must be that plus that is going to appear to be walking at 37 metres per second. Relative to train B, so assuming train B was still travelling at 10 metres per second in the opposite direction, then it would appear to be 37 metres per second east minus the 10 metres per second west, which would be 47 metres per second east. You might want to write that down on paper and see that you can calculate that properly, and if you're not sure, check with me when we get to class. So that's all good and well for simple straight line examples, but is it possible to do relative velocity in 2 dimensions? So we've got two cars, they're travelling at right angles. So car A is 25 metres per second east, car B is 20 metres per second north. Find velocity of B relative to A. So subscript BA means B relative to A. And the simple way to remember then is B will be minus the A. So just keep that order the same. So we've got velocity of B minus the velocity of A. Doing vector addition, so rotating that, adding it on, we've got that plus that. Our resultant vector would be this vector here. If we calculate that, it would be 20 squared plus 25 squared, and take the square root, somewhere in the vicinity of, I don't know, let's take a guess, 33. Having just done that on the calculator, 32, so not far off. The only thing that I'm missing now for my velocity would be to give myself an angle so that I can actually give myself a bearing. That could be an angle right round here, so a true bearing, or a north something west angle. And simple bit of trig using inverse tan would be able to solve that for you. That's it. We'll have a look at some more problems in class.